नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE एंड नीट। यह मॉलिकुलर ऑर्बिटल का सेकेंड एपिसोड है और आज हम इसमें लीनियर कॉम्बिनेशन ऑफ एटॉमिक ऑर्बिटल्स ऑफ होमोन्यूक्लियर डायटोमिक मॉलिक्यूल्स और आयंस के बारे में डिस्कस करने जा रहे हैं। टुडे वी आर गोइंग टू डिस्कस linear combination of s orbitals only, means we are going to cover up to beryllium molecule. We are going to learn how to decide that a molecular orbital is Gerade or ungerade. So in the last class we have discussed about the difference between valence bond theory and molecular orbital theory. In case of molecular orbital theory, there is linear combination of atomic orbitals. So here we are discussing about those combinations one by one. Like today we are going to discuss the combination of SS atomic orbitals to form molecular orbital. So in SS combination we are going to cover hydrogen molecule, helium molecule and lithium molecule. So if one of the wave function is arbitrary assigned a positive sign, the other may be positive or negative. The meaning of this statement is that if two atomic orbitals are going to combine, either they are going to have a destructive interference or they are going to have a constructive interference. So let us start by taking a hydrogen molecule. So in this hydrogen molecule, here it is shown that 1s orbital of one hydrogen atom has positive sign and another hydrogen atom 1s orbital is there, it has negative sign. This positive and negative sign indicates that they are in opposite phase. So when they are going to combine, there is a destructive interference. So in this destructive interference, this molecular orbital is formed. So if you see this molecular orbital, this black colored dots are representing the nuclei of two hydrogen atoms and this is electron cloud. In this molecular orbital, we can see that the electrons are away from the nucleus in both these orbitals and the nuclei is near to each other. So when the nuclei is nearer to each other, repulsive forces will dominate. So here, because of that, the system, if I compare the energy of this molecular orbital with respect to the energy of individual atomic orbitals, the energy of this anti-bonding molecular orbital is greater than that of individual atomic orbitals. And here in this graph we can see that how the wave functions are changing. This is the nuclei of one atom and this is the wave associated with 1s atomic orbital. So it is symmetric about this nucleus, wave associated with 1s atomic orbital. We can say that this is telling about the probability density on this curve. Same way, since the other atomic orbital is in opposite phase, this is the nuclei of that atom, hydrogen atom, and this is the distribution of electron density near the nuclei of that hydrogen atom. Now when these hydrogen atoms are coming nearby, if they are in opposite phase, these waves are going to cancel out each other, and particularly at this position we can see that there is a node. So in this diagram, if we see in this diagram, we can check that this point is a node. So in this diagram, this is a node. This is anti-bonding molecular orbital, and in sigma, because this is linear combination, head-on combination of atomic orbital, due to head-on combination sigma molecular orbital is formed. That's why it is denoted by sigma. So sigma 1s star is for anti-bonding. So 1s is this molecular orbital is formed by the combination of two 1s atomic orbital, and this sigma is denoting that there is head-on collision. So this is anti-bonding molecular orbital. Same way, if we see that these two atomic orbitals of two different hydrogen atom, this 1s atomic orbital and this one atomic orbital, if they are in same phase, they have positive sign. So there is constructive interference. Constructive interference means what? This is the nuclei of two hydrogen atoms and most of the time the electron is between them. When the electron is between them, the force, because both the nuclei is going to attract that electron, it means that the force of attraction will be more, the system is going to release more energy, the system is going to stabilize. So if I compare this bonding molecular orbital, sigma bonding, sigma means here 1s orbital is going to overlap, and this is end to end overlapping. So because of that, sigma bond is forming. This bonding molecular orbital has no nodal plane, because whenever we have to see the nodal plane, we have to see the nodal plane between these two nuclei, and there is no place where the electron density is 0. So we can say here that there is no nodal plane in sigma 1s molecular orbital. And here is the diagram. This is the nuclei of one atomic orbital, and this is the probability density associated with that. So on both sides, since probability density is probability of finding electron at a point in three-dimensional space, it is always positive. And for the other nuclei, this is the nucleus, and this is the distribution of probability density. So both are hydrogen atom, 1s atomic orbital is there. Now if they are going to constructive interference, then the probability of finding electron, this wave, the probability electron density in between these nuclei is going to increase, and the probability density away from the nuclei is going to decrease with respect to between the nuclei of these two atoms. So we can say that in bonding molecular orbital, the probability of finding electron is more between the two nuclei, and because of that, the force of attraction is increasing, and the system is releasing more energy, and system is getting stabilized. So in terms of energy, we can say that the energy of sigma bonding molecular orbital is less than the energy of pure atomic orbital. So here, if we see in terms of energy, when a pair of atomic orbitals combine, they give rise to a pair of molecular orbitals. We know that number of atomic orbitals combined is equal to the number of molecular orbital forms. The number of molecular orbitals produced must always be equal to the number of atomic orbital combined. Here in this, on y-axis, this y-axis is related to energy. So this is energy axis, and here we are comparing the energy of the molecular orbital form with respect to the initial energy of atomic orbital. So this is 1s atomic orbital, pure atomic orbitals are there before linear combination. Now due to combination of atomic orbitals, this is sigma 1s bonding molecular orbital, and this is sigma star 1s anti-bonding molecular orbital. The energy of bonding molecular orbital is less than the energy of pure atomic orbitals, and the energy of anti-bonding molecular orbital is greater than the energy of pure atomic orbitals. And now we are going to fill electrons into these molecular orbitals. They will follow the same rule as we are using for filling the electrons in atom. We are following certain rules. Those rules will be followed here. So there are total 2 electrons, 1 electron from each atom. So we first fill the lower molecular orbital, and each molecular orbital will occupy 2 electrons, and those electrons should be of opposite spin as we are following in atomic orbitals. That's why we can say here that these 2 electrons are there in molecular bonding orbital. From here, from this diagram, we can calculate what is bond order. So bond order is defined as half times the number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital, and this bond order is very relevant. If the bond order is 1, we can say that 1 bond is there. If bond order is 2, we can say 2 bonds are there, and if bond order is 3, we can say that 3 bonds are there between 2 atoms. So higher the value of bond order is directly proportional to bond energy, and bond order is inversely proportional to bond length. So we are going to study about the bond order of this hydrogen molecule. So in case of hydrogen molecule, there is no electron in anti-bonding. Anti-bonding is empty. There are 2 electrons in bonding molecular orbital. So from there we can calculate the bond order is equal to 1. And we also know from valence bond theory that if a hydrogen molecule will be formed, there is one single bond between 2 hydrogen atoms. So it's matching with the result of valence bond theory also. And here we can say that since all these electrons are paired, the molecule is diamagnetic. So we can say about the diamagnetic behavior. Valence bond theory cannot explain about the stability of H2 plus ion, because in valence bond theory we cannot not discuss about the chemical species having odd number of electrons. So that is one of the demerit of valence bond theory, which we can discuss here in molecular orbital theory. So here, if by applying molecular orbital theory, we can say that the total number of electrons in H2 plus is 1. So we can calculate what is bond order. If only one electron is there, then in bonding molecular orbital we can fill one electron. There is no electron in anti-bonding, so we can calculate bond order is equal to half times of 1 minus 0, which is equal to half. So bond order is positive. If the bond order is positive, it means that the chemical species can exist. But if the bond order is 0 or negative, it means that the chemical species cannot exist. So we can say that H2 plus ion can exist. So here we can say that hydrogen is diamagnetic, but H2 plus is paramagnetic. The magnetic behavior of a molecule, diatomic molecule, and a diatomic ion can be explained with the help of molecular orbital theory. So about H2 plus ion, we can say that this may be considered as a combination of hydrogen atom and H plus ion. This species exists but not common, since H2 molecule is more stable. H2 plus exists, but it is not that stable as H2 molecule. There is a question about ions of hydrogen molecule. So let me read this question. Bond order of H2 plus ion and H2 minus ion is same, but which is more stable? So here we have explained that in case of H2 minus, the total number of electrons will be 3. So if we fill in molecular orbital theory, according to this energy diagram, there are 2 electrons in bonding molecular orbital and there is 1 electron in anti-bonding molecular orbital. So if I calculate what is the bond order in H2 minus molecule, that is equal to half times of 2 minus 1, that is half. Same way if I calculate, because in H2 plus we have already done that its bond order is equal to half. There is no electron in anti-bonding, there is only 1 electron in bonding. So from here we are saying that anti-bonding has more energy, so bond order is same, but H2 plus is more stable than H2 minus, because in H2 minus there is 1 electron in anti-bonding molecular orbital, while in case of H2 plus there is no electron in anti-bonding molecular orbital. Today we are going to discuss about Gerade and ungerade molecular orbitals in hydrogen molecule. So there are two methods to decide that an molecular orbital is gerade and ungerade. The first method is very simple. The molecular orbital are gerade and ungerade on the basis of center of inversion. That is, if the sign of wave function is unchanged when the orbital is reflected about its center, then the orbital is gerade. If it is changed, then it is ungerade. What is the meaning of these statements? Suppose these are our orbitals, anti-bonding and bonding molecular orbitals. So what we are discussing here, that the center of this anti-bonding molecular orbital, we are discussing about this anti-bonding molecular orbital, the center of this, because we know that there is a nuclei over here and there is a nuclei over here. So the center of this is this nodal plane. So if we are moving about this center of anti-bonding molecular orbital, we are taking a reflection. Suppose if I am taking this as a point, and if I want to take reflection about this point, then the reflection point will be here. So the sign of the wave on the left hand side is positive, on the right hand side is negative. If I take any point and if I take reflection of that through this point, if the sign will change, we'll say that it is ungerade. So from this logic, that find out the center of the molecular orbital, and if you take a point on left hand side and take a reflection on the right hand side, and if the sign of waves get changed, then it is anti-bonding or it is ungerade molecular orbital, not anti-bonding, it is ungerade molecular orbital. If the sign is not going to change, it will be gerade. For example, in this bonding molecular orbital, there are two nuclei which is not shown here. So let me show these nuclei. This is one nuclei and this is the other nuclei, and this is the center of this bonding molecular orbital. So now if I take any point on the left hand side and if I go through this center, so the sign here is positive and the sign here is also positive, because we know that everywhere the sign is positive due to constructive interference. So we are moving through the center, that is center of inversion, and the sign remains same, then we'll say that this is gerade. So in case of SS overlapping or in case of SS linear combination of atomic orbital, sigma anti-bonding molecular orbital is ungerade and sigma bonding molecular orbital is zerade. This is a very simple method to find that an orbital, molecular orbital, is zerade and ungerade. We are going to practice the same thing in case of sigma 2p linear combination, or there is another method which is known as method 2. So in case of method 2, what we are doing, there are 3 steps involved. Rotate the orbital about the line joining the 2 nuclei. So we have to rotate this orbital, molecular orbital, along the line joining the nuclei, and then the line perpendicular to this. So we have to do 2 times rotation. If the sign of the lobe remains the same, the molecular orbital is zerade. If the sign of the lobe get changes, the molecular orbital is ungerade. So again, we are taking some example to explain this. This is sigma 1s bonding molecular orbital. So everywhere I have made 2 positive sign, one at the top and one at the bottom, in order to show, because I have taken the lower one a thin positive sign and the upper one is a thick positive sign. If I am going to rotate this about the internuclear axis, right? So if I rotate this by 180 degree, this lower thin plus sign will go up. So after rotation, we can see here that this lower thin point is up and thick point plus point is down, right? And we know that basically this thin and thick plus both are same, but in order to show you that on rotating about the internuclear axis, there is no change in the sign of the orbital. It is positive. This is the first step. Then what we are going to do, that we are going to rotate about another perpendicular axis. So I can take an axis which is passing through the plane of paper and perpendicular to it. So if I rotate by 180 degree, means what basically I am doing, that I am just placing this rectangle here about some axis which is perpendicular to the plane of this paper, right? So if I just put this on the right hand side, then what will happen? The thin plus will be at the top only and the thick plus is at the top only. So there is no change in sign about the rotation of this molecular orbital along the line passing through the nuclei of 2 atoms, as well as another line perpendicular to it. So if there is no change in sign, we'll say that this is Gerade. Sigma 1s molecular orbital is Gerade, and we can see here that in this molecular sigma molecular orbital between the nuclei of 2 atoms, there is no region where electron density is 0. So there is no nodal plane in case of sigma 1s molecular orbital. Now for anti-bonding molecular orbital, what we are doing here, that the sign on the left hand side, we put a thick and thin positive sign in order to just show you the distinguished thing which we are able to see on this paper. So otherwise both signs are same, but in order to distinguish that we are rotating about the internuclear axis, we are doing same. On the right hand side, I have put a thick and thin negative sign on top and bottom. So now I'm going to rotate about this internuclear axis. So when we are rotating this about the internuclear axis, we can see here that the thick sign is on the right hand side lobe, thick sign is below negative sign, and thin is above, and same way here positive and negative. So now if you see, there is no change in sign, because initially also on the right hand side lobe negative sign is there, on the left hand side lobe positive sign is there, still that is the same. Now what we are doing, that again we are taking a plane which is perpendicular to the plane of paper. So about this plane, I am doing that I am rotating this whole plane by 180 degree, right? Rotating this whole plane by 180 degrees. So here on rotating by 180 degree perpendicular to the plane, what we are going to get here is this left hand side lobe will come on the right. So this is now 2 lobes. The upper lobe will be same, that is thin positive sign, lower is thick positive sign, and the left hand side lobe will be negative. So now we can compare first diagram and second diagram. Now you can see that if we are passing through the internuclear axis, the sign of the lobes get changed. Initially it was negative sign and now it is positive sign. So from here we can decide that this anti-bonding molecular orbital 1s is ungerade. So this is a little bit lengthy, not difficult, but little bit lengthy method. The first one is more easy, that we have to find out the internuclear axis and then the center of that internuclear axis about that center, if we take a point on the left hand side and we find reflection on the right hand side, if the sign of wave will be same on both sides, then we'll say it is Z-ray, and if it is different, we'll say it is ungerade. So this is the way to find out. Now in this we can see that sigma star antibonding molecular orbital is ungerade and it has one nodal plane. We can find out this plane is nodal plane, right? So electron density on the left hand side is going to finish here and the right hand side is going to finish here. So this is the plane on which there is no probability of finding electrons. So this is a nodal plane. So there is one nodal plane in sigma 1s star or sigma 1s antibonding molecular orbital. The second example of SS linear combination is helium molecule, He2 molecule. So we know that there are two helium atoms. These helium atoms are undergoing linear combination to form molecular orbitals. So since there are two atomic orbitals going to combine, so there is formation of two molecular orbitals, sigma 1s and sigma star 1s. Sigma molecular orbital is formed due to head-on collision. So when 1s atomic orbital of helium atom is going to linear combination with another 1s atomic orbital of helium atom, there is formation of sigma 1s and sigma star 1s molecular orbitals. Now if we see that what is the electronic configuration of 1s atomic orbital, in helium there are two electrons, another helium atom there is two electrons. So the 1s atomic orbitals are fulfilled. Since the number of atomic orbitals is equal to the number of molecular orbitals formed, if all the atomic orbitals are fulfilled, it means that the molecular orbitals are also fulfilled. We can see here that there are two electrons in bonding molecular orbital and there are two electrons in anti-bonding molecular orbital. So for helium, if we calculate that what is helium molecule, if we calculate that what is the bond order is equal to half times the number of electrons in bonding minus number of electrons in anti-bonding, which is equal to 0. We know that when the bond order is 0 or negative, the chemical species cannot exist. So helium molecule does not exist. But for helium 2 plus ion, we are counting the number of electrons in helium 2 plus ion, that is equal to 3. So if we calculate and we are removing the electron in helium 2 plus 1 electron from anti-bonding will be removed, then helium 2 plus ion will be formed. So in this, if we calculate what is the bond order, that is half times of 2 minus 1, that is equal to half. Since bond order is positive fraction, so if bond order is integer or positive fraction, the molecule can exist. So we can say that helium plus ion exists and there is experimental evidence of helium 2 plus ion at very low temperature and low pressure. Now we can compare similar to hydrogen molecule. We can say that sigma 1s bonding molecular orbital is Z-rate and sigma star anti-bonding molecular orbital is ungerade in both helium molecule and helium 2 plus ion. Since helium molecule does not exist, that's why we are talking about in helium 2 plus ion. If we have to find Z-rate and ungerade, the method will remain same. That from the center of molecular orbital, if we take on the left and right hand side, if the sign of wave will be same, then we'll say it is Z-rate. If it is opposite, then we'll say it is ungerade. So here now we can compare certain chemical species which can exist in nature. So we are comparing these four chemical species which are formed by SS linear combination of atomic orbital. The first molecule is H2 plus, or the first ion is H2 plus, then hydrogen molecule, then helium ion, and then helium molecule. We know that helium molecule does not exist, so there is no meaning of bond order, bond length and bond energy. But for helium molecule, helium ion, but for helium ion we have calculated that there are total 3 electrons, 2 electrons in bonding, 1 electron is anti-bonding, so bond order is half. For hydrogen molecule there are only 2 electrons in bonding, so bond order is 1. For H2 plus ion there is only 1 electron in bonding, so bond order is half. So the first thing is we have to relate helium ion and hydrogen ion. So for our first question is about helium ion and hydrogen ion, both have bond order of half. But now we can say that which is more stable, right? About helium ion and hydrogen ion. In helium ion there is 3 electrons, 1 electron is present in anti-bonding, while in case of hydrogen ion there is no electron in anti-bonding. bonding. So that's why the bond energy of hydrogen ion should be greater than the bond energy of helium ion. And if I compare hydrogen molecule and hydrogen ion, in order to form hydrogen ion, we are removing one electron from bonding molecular orbital. So bond order of hydrogen molecule is 1, but bond order of hydrogen ion is half, and because of that we can say that the bond energy of hydrogen molecule is greater than the bond energy of hydrogen ion. And same way we can compare the length, right? So here since the bond order of hydrogen molecule is highest, so its bond length will be minimum. Among plus and H2 plus, we are removing one electron from anti-bonding. So if we compare the bond length of helium 2 plus ion is greater than the bond length of H2 plus ion. So this is the order of bond length. Similarly, when we are talking about lithium molecule, lithium atom has an electronic configuration of 1s2 2s1. So the valence electron is present in 2s atomic orbital, and this 1s is completely filled. This is inner atomic orbital. So here if we see overall energy of molecular orbital formed, so due to linear combination of atomic orbitals, lithium in 1s, so lithium 1s is completely filled. So that's why the sigma 1s molecular orbital and sigma star 1s molecular orbitals are completely filled, and they are going to cancel out each other. So there is no contribution of 1s in bond order of the molecule. If we are discussing about 2s, there is one electron in 2s and one electron is 2s. So the total number of electrons in sigma 2s will be 2. There is no electron in anti-bonding. So if we calculate the bond order, either we'll calculate the bond order with respect to the valence electrons, or if we calculate with respect to the total number of electrons, the answer will be same. So here this is the electronic configuration of lithium molecule, and in this we have calculated bond order. So bond order is half times bonding electrons is 4 and anti-bonding electrons is 2, so the bond order is 1. Or we can say that from valence electrons also we can calculate half the number of bonding molecular orbital, number of electrons in bonding molecular valence orbital is 2, and there is no in anti-bonding. From there also the bond order is coming to be 1, and from here there is no unpaired electron, so we can discuss about the magnetic behavior. So lithium molecule is diamagnetic in nature, and this is the linear combination of atomic orbitals. So here we are more interested in valence atomic orbital. So we can say that this is 2s and this is 2s, and this positive sign indicates that these atomic orbitals are in same phase. Due to constructive interference, molecular orbital will form. Now if we have to find that how this molecular orbital is zeroed, that is very simple. These are the nuclei of two atoms, and now this is the center. So center of inversion means if I take any point in this molecular orbital, and through the center of this molecular orbital, if we go in opposite direction, reflection of this point, if the sign here is positive and here also is positive, we'll say that it is a Gerade molecular orbital. Same way, when these two 2s atomic orbital of lithium undergoing destructive interference, positive and negative sign indicates that there is destructive interference. So because of that, anti-bonding molecular orbital is forming. This is head-on collision. So sigma molecular orbital is going to form, and they have mentioned here ungerade. That is very simple. This is nuclei of one atom and this is another atom, and the center of this is this point here where nodal plane is passing through it. So if I take any point in the left hand side lobe and pass through this center of this molecular orbital, then the other side, if the left hand side is positive, the right hand side is negative. So the sign of wave is changing, right? If I move in any direction, if the sign of wave is changing, then we can say that it is anti-bonding molecular orbital, and anti-bonding molecular orbital here is ungerade. So in sigma, anti-bonding molecular orbital is ungerade. And this is the second wave. It is lengthy, but you can see that what we are doing, that we are rotating about the axis passing through the nuclei of two atoms, and because of that this positive sign in up and down changes position, but we know that this positive and this positive in up and down is same. So there is no change in sign on rotation about the internuclear axis. Then we are going to rotate this whole molecule to a line perpendicular to internuclear axis. So by doing that, suppose if I am taking this point and this is the plane, this whole plane we are discussing. So if we rotate about an axis shown here, so what will happen that on rotating about this axis, this molecular orbital, now this point here will be seen at this point, and the sign of waves is the same on up and down on the opposite side of this internuclear axis, right? So sign here and sign here is same, this and this is same, so we'll say that it is Z-ray. So this sigma 1s molecular orbital is Z-ray in nature. Same way we have discussed that, and by looking the diagram we can say that again there is no nodal plane in this sigma molecular orbital. So same way we can find out for anti-bonding. In case of anti-bonding, you can see here that on the right hand side the sign is negative. When we are rotating about internuclear axis, this will form, so there is no change in sign. Now if we rotate a line perpendicular to internuclear axis, so we can say that this point is going here, and if I compare the first figure and the third figure, we can say that the sign of the lobe on the right hand side initially was negative, now it is positive. So the signs are changing here, so we'll say that it is ungerade. So sigma anti-bonding molecular orbital is ungerade, and we can find out the number of nodal plane. Nodal plane, whenever we have to find out in a molecular orbital, we have to find the nodal plane between the nuclei of two atoms. So this is the plane which is perpendicular to this plane of paper, and it is passing through this point which is a midway between the nuclei of two atoms, where the probability of finding electron is 0. So we can say that in anti-bonding sigma molecular orbital there is one nodal plane. So same way we can find bonding molecular orbital. We are discussing about 1s, but we know that for 2s also the same similar things are there, so that is nothing new. I have discussed the same point. Now in case of lithium molecule, we are saying that lithium molecule is stable, but because we have calculated the bond order is equal to 1, so lithium is a stable molecule, has lower energy than two separated lithium atoms. However, this does not mean that lithium 2+ is most stable form of elemental lithium, because lithium is a metal and in nature it exists in the form of solid. In fact, at normal temperature and pressure, lithium exists as a solid containing many lithium atoms bound together, which we are studying in metallic bond. So definitely lithium 2+ ion is stable, but it is not the stable form of lithium atom. So in nature lithium is existing in the form of solid. Same way we can discuss about beryllium molecule. So in case of beryllium atom, the electronic configuration here again as orbitals are involved, 1s2 and 2s2. So we can say that all the atomic orbitals are fulfilled. So molecular orbitals formed by the linear combination of these atomic orbitals should also fulfill. Here we have written the electronic configuration. In sigma 1s molecular orbital there are 2 electrons, then sigma star 1s 2 electrons, sigma 2s 2 electrons, sigma star 2s 2 electrons. So if I calculate what is the bond order, so there are 4 electrons in bonding and 4 in anti-bonding, so bond order is 0. If bond order is 0, it means that beryllium molecule does not exist, and it is correct. In nature we are not finding beryllium molecule. So beryllium molecule does not exist, but beryllium metal contains many beryllium atoms. Beryllium metal contains many beryllium atoms bonded to each other and is stable, and we know that beryllium exists in metallic form in which many atoms are there together. So here we can learn about two things: highest occupied molecular orbital, the energy diagram for lithium molecule. Suppose here we have taken an example of lithium molecule. So this is the highest occupied molecular orbital, highest occupied molecular orbital, or sigma star 2s. In terms of energy, this is the first orbital which is unoccupied, so we can say that this is lowest unoccupied molecular orbital. So these are the terms which we can use in question, that highest occupied molecular orbitals and lowest unoccupied molecular orbitals. If you are liking this information, please like, subscribe and share for the third episode of molecular orbital theory. Thank you.